there is a new principle, that is argument principle, which is very important and expected one. Let's start with this. Very important remarks for you. In the last video, I have discussed these remarks which are very helpful in proving this argument principle. So first one is, if fz is a non-constant function, analytic at z0 with f of z0 equal to 0, then f dash z over fz has a simple pole at z0. So we are having fz to be a non-constant function which is analytic at z0, and f of z0 equal to 0 means it is having 0 at z0. Then f dash z over fz has a simple pole at z0. So we are having a simple pole at z0 for f dash z over fz. Remember this. Second, if fz has a 0 at z0 of multiplicity alpha, then we know that residue of f dash z over fz is equal to same, that is alpha. So when we talk about the multiplicity, we are having the same number as the residue, that is alpha. And if we are talking about the order of the pole, then the residue will be negative of that number. Let's see the third remark. If fz has a pole of order beta, then residue of f dash z over fz at z equal to z0 is minus beta. That means the negative of the order number. Fourth, if fz has number of zeros n1 and gz has number of zeros n2, then their product has number of zeros as n1 plus n2. Is this clear? Obviously, the number of zeros will be their sum. Fifth, log of fz is equal to log of mod fz plus iota argument fz. This is a result. And now we are having a definition. The net change in argument fz as z traverses a contour C is called the variation of argument fz along C and is denoted by delta C argument fz, where delta C is the variation of argument fz. Now let's start with the theorem, that is the argument principle. Let fz be analytic inside and on a simple closed contour C except for a finite number of poles inside C. And suppose fz is non-zero on C. What it is saying that you have a function fz which is analytic inside and on simple closed contour C. Suppose this is your closed contour C, and the function is analytic inside and also on this simple closed contour C, except for the finite number of poles inside C. That means if you are having the finite number of poles, suppose these are your poles. Except these poles, everywhere function is analytic, right? And fz is non-zero on C. If n and p are respectively the number of zeros and poles inside C, then now the number of zeros are given to be n and the number of poles are given to be p, right? Then we have 1 over 2 pi delta C argument fz is equal to number of zeros minus number of poles. This is your argument principle. So let's prove this. Suppose that zeros of fz within C occurs at z1, z2, z3, zn with their multiplicity, suppose alpha 1, alpha 2, alpha 3, alpha n, right? And let number of poles of fz within C occurs at w1, w2, w3, wm of order beta 1, beta 2 up to beta m. Suppose. Now this is very important. Then number of poles of f dash z over fz within C occurs at. Yes, tell me. Right now we have read that number of poles of Fz occurs at W1, W2, W3, Wm up to so on, right? So we are having the poles at W1, W2, W3 up to Wm. Of course, we are having the poles at these points. But they are talking about the poles of F-Z over Fz. Any other poles we are having? Just recall your remark number 1. Let's recall remark number 1. If Fz is non-constant function, analytic at Z0. See, analytic at Z0 with Fz0 equal to 0. That means it is talking about the point Z0 to be as a 0 of Fz. That means at zeros, we are having simple pole. So F dash Z over Fz has a simple pole at Z0. What is Z0? Nothing but the 0. It is nothing but the 0 of Fz. That means whenever we are having the zeros of Fz, that zeros are actually the simple poles of F dash Z over Fz. So let's go back to our proof. So it is saying that the poles of F dash Z over Fz within C occurs at, yes, now tell me. Yes, they are also occurs at number of zeros. That means they are also occurring at Z1. Oh, sorry, oops. I'm very sorry for this. So they are also occurring at Z1, Z2, Z3, up to so on Zn. And of course W1, W2, W3 up to Wm. So we are having total number of poles as this, and all of them are simple, right? Alright. Second, now what is the residue of F dash Z over Fz at these poles? Whenever we are talking about the poles and they are also having the order beta, beta 1, beta 2, beta 3 up to beta m, then what will be the residue? The negative of order. That means minus beta 1, minus beta 2, minus beta 3, right? And any other residue? Of course, when we talk about the multiplicity, we are having the same residue as alpha 1, alpha 2, alpha 3, alpha n. Check your recall remark number 2 and remark number 3. Whenever we are having the multiplicities, we are having the same value of the residue of F dash Z over Fz as the multiplicities, and we are having the values of residue at F dash Z over Fz as negative of the orders of the poles. So what are the total number of residues we are having at these points? So this is equal to the residues of F dash Z over Fz equal to alpha 1, alpha 2, that is your multiplicities up to alpha n, plus minus beta 1, minus beta 2, minus beta 3 up to minus beta m, right? The negative of the orders of poles. So these are all over the total residues we are having. Now by Cauchy residue theorem, we have integral over C F dash Z over Fz is equal to. In the last video, we have done the Cauchy's residue theorem. What this integral equal to? It is 2 pi iota, sorry, 2 pi iota into the sum of the residues. Now sum of the residues means we take the sum of this as summation alpha I, where I going from 1 to n, and also the summation of this, but we are having the negative sign, so I present negative here with summation beta I, where I going from 1 to m, right? So this is equal to further 2 pi iota alpha I, nothing but the number of zeros, betas, nothing but the number of poles. Is it clear? Alright. Now we know that log of fz is equal to log of mod fz plus iota argument fz, where fixed branch of log is chosen over here. Now we have to, this is, you just mark this as your 1, and now I am integrating the left hand side. Right hand side I get the result, left hand side I am integrating now. What is integral over c f dz over fz dz is equal to? It is, yes, integration for this is log of fz over the contour C. Now because it is a closed contour and it is having the same initial and final points, before putting the values or before getting this, solving this, we have to use a result. What is log of fz? It is log of mod fz, yes, plus iota argument of fz. Now if suppose I have the values for the integral, because it is a closed contour and having the same initial and final points, when we put up the values, that is final value minus initial value, because both these final and initial points are same, so this will be 0 plus iota. Now this is nothing but the variation of, yes, just now we have read, it is nothing but the variation of argument fz. So it is delta c, it is the variation of argument fz, right? Okay, mark this as your 2. And thus we say that from 1 and 2 we get iota delta c argument fz is equal to 2 pi iota n minus p. Just cancel iota iota and you will get n minus p as 1 over 2 pi delta c argument fz. This is your argument principle, that is the number of zeros minus the number of poles is equal to 1 over 2 pi delta c argument fz, where delta c argument is the variation of argument of fz. There is a remark. Let fz be analytic inside and on a simple closed contour C having n zeros inside C but no zero on C. Then, according to argument principle, we have 1 over 2 pi delta C argument fz is equal to n minus p. But where are p? We don't have any poles. So poles are not mentioned in this remark. So if we are not having the poles, then we say that argument principle as 1 over 2 pi delta c argument fz is equal to n only, right? This is just a small remark. Now a very interesting lemma is there, a short lemma. Suppose fz and gz are analytic inside and on a simple closed contour C with fz and gz are non-zero on C. Now both these are non-zero and both are analytic inside and also on closed contour C, so we can apply argument principle over here, right? Then it is saying that you have to prove delta C argument fz gz, that means their product is equal to sum of their arguments, delta C argument fz plus delta C argument gz. Now because we are having the two functions which are analytic inside and on closed contour C, let's suppose that number of zeros of fz is n1 and number of zeros of gz as n2 respectively inside C, right? Then by the arguments principle, we have, just now we have read this remark. I'm using this remark now. I'm not having poles, so I'm using the remark for the number of zeros only. So if n1 is a number of zeros, what I'm getting that? n1 is a number of zeros for fz. So I write by this remark, by argument principle, 1 over 2 pi delta C argument f of z is equal to n1. This is for fz, and for gz I should write 1 over 2 pi delta C argument of gz, which is equal to n2. Very clear? Now since the product fz into gz has how many number of zeros? Obviously n1 plus n2. Should I explain this? Alright. Suppose you are having fz to be equal to suppose z minus 1. So it is having the number of zeros as 1 only. So it is having number of zeros as 1. Suppose gz is equal to z minus 1 and z minus 2 and z minus 3. How many number of zeros we are getting for gz? Yes, 1, 2 and 3. We are getting 3. Suppose now I say that fz into gz, which means, right, I take this at z minus 4. So which means how many factors I am having now? Z minus 1, Z minus 2, Z minus 3, Z minus 4. Now what are the number of zeros for fzgz? It is, yes, 4. 1, 2, 3, 4. Right? So this is nothing but the sum of fz plus gz. So number of zeros of product fzgz is equal to sum of the number of zeros for fz plus number of zeros for gz. I think this is very clear to you. Why I think it is clear to you. Alright. So fzgz has n1 plus n2 zeros inside C, right? Now I'm using the argument principle for fzgz. So this is equal to, by argument principle, I'm having 1 over 2 pi delta C argument of fz gz. This should be equal to the number of zeros, which are n1 plus n2. And yes, n1 is nothing but delta C argument of fz 1 over 2 pi plus n2 is nothing but 1 over 2 pi delta C argument of gz. Right? Take this 1 over 2 pi, cancel on both the side. You will get finally delta C argument fzgz is equal to delta C argument fz plus delta C argument gz. Very, very important. Alright guys, thank you for watching this video. We will be meeting in the next video. Do subscribe my channel for the latest videos, and now next time we are going to start Rauchi's theorem. Just get ready for that. Alright, goodbye.